Good afternoon, everyone. My name is ABISHAI ARBOLLENTE, and my topic for today's video is Mathematical Language and Symbol Variables. Variable. A variable is a placeholder for an unknown quantity in math. Variables are used to find general equations and then later substitute in specific values for the variable. Most of the time, variables are represented by lowercase letters such as x, y, and z. Advantage of using variables. They allow mathematical ideas to be communicated clearly and briefly. The equation 2x2 plus y equals 6 is much clearer than the equivalent phrase 2 times some number times itself plus some other number is equal to 6. Variables also make mathematics more generally applicable. Example. To illustrate the second use of variables, consider the statement, no matter what the number might be chosen, it is greater than 2. Then square is greater than 4. In this case, the variables enables you to maintain the generality of the statement and replacing all the instances of the word it by the name of the variable ensures that possible ambiguity is avoided. No matter what number n might be chosen, if n is greater than 2, the n squared is greater than 4. Writing sentences using variables. Use variables to rewrite the following sentences more formally. Are there numbers with the property that the sum of their squares equals the square of their sum? Solution. Are there numbers a and b with the property that a squared plus b squared equals a plus b squared? Or are there numbers a and b such that a squared plus b squared equals a plus b squared, or there exists any number a and b such that a squared plus b squared equals a plus b squared. Example number 1, solution B. Given any real number, its square is non-negative. Solution B. Given any real number r squared is non-negative. Or for any real number r squared is greater than 20. For all real numbers, r squared is greater than 20. Some important kinds of mathematical statement. Three of the most important kinds of sentences in mathematics are universal statement, conditional statements, and existential statements. A universal statement says that a certain property is true for all elements in a set. For example, all positive numbers are greater than 0. A conditional statement says that if one thing is true, then some other thing also has to be true. For example, if 378 is divisible by 18, then 378 is divisible by 6. Given a property that may or may not be true, an existential statement says that there is at least one thing for which the property is true. For example, there is a prime number that is even. Some important kinds of mathematical statement. Universal condition statements. Universal condition statements contain some variation of the words for all, and conditional statements contain versions of the words if then. A universal conditional statement is a statement that is both universal and conditional. Here is an example. For all animals A, if A is a dog, then A is a mammal. One of the most important facts about universal conditional statements is that they can be rewritten in ways that make them appear to be purely universal or purely conditional. Universal existential statement. A universal existential statement is a statement that is universal because its first part says that a certain property is true for all objects of a given type. And it is existential because its second part asserts the existence of something. For example, every real number has an additive inverse. In this statement, the property has an has an additive inverse applies universally to all real numbers. Has an additive inverse asserts the existence of something an additive inverse for each real number. However, the nature of the additive inverse depends on the real number. Different real number have different additive inverses. Existential universal statement. Is an existential universal statement is a statement that is existential because its first part asserts that a certain object exists and is universal because its second part says that the object satisfies a certain property for all things of a certain kind. There is a positive integer that is less than or equal to every positive integer. This is only an example. This statement is true because the number 1 is a positive integer and it satisfies the property of being less than or equal to every positive integer. Some of the most important mathematical concepts, such as the definition of limit of a sequence, can only be defined using phrases that are universal, existential, and conditional. And they require the use of all three phrases for all: there is and if then. Given problem statement, are there numbers whose square are smaller than the numbers themselves? The real number x such that x squared less than x squared represents the square of x. Example, statement is true when a problem of 1, for example, x equals 1/2, x squared equals to 1/2 equals to 1/4 less than 1 squared equals x. Thus, we then note that x squared less than x is true for x equals to 1/2. This is the given question for me. And the statement number 2, B. P represents to prime number is an integer P greater than 1. P has only 2 division are necessary 1, and P itself since every number is divisible 1 and itself. Example, P equals 5, P greater than 1, 5 greater than 1 equals first condition, 5 has divisible only 5 and 1. And that's all. Thank you for listening.